All right, so let's get started. Last time, we looked at a C infinity vector bundle over a manifold. And we defined integration along the fiber, pi lower star, from forms with compact support in the vertical direction to forms on M, okay? And we show that it commutes with the exterior derivative up to sine. So we show d pi lower star is pi lower star d, but with the sign -1 to the r. And I said that this sign makes sense because pi lower star has degree -r, and d has degree 1. And in general, when you work with graded mathematics, if you interchange two objects, there's a sign, and the sign is -1 to the product of the degrees. So the sign should be -r times 1, and that's the same sign as -1 to the r, okay? Okay, but because of this, pi lower star induces a mapping cohomology. So pi lower star induces pi lower hatch in the cohomology with compact vertical support of E to the cohomology of M, okay? And the Thom isomorphism theorem says that this is an isomorphism for a manifold of finite type, okay? So, Thom isomorphism theorem says pi lower star is, pi lower hatch is an isomorphism for M of finite type. Okay. And the reason we need finite type is that the proof, is using the Maya-Vittora sequence, by inducting on the number of open sets in a good cover, just like before. But again, you can ask, like, is this, is that really necessary? You need that hypothesis for the proof, but, is there a different proof that maybe doesn't require this hypothesis? Now, for, like the other theorems, like the Kunis formula and maybe some other theorem, right? We had counterexamples when M is not of finite type. But for this theorem, actually, this hypothesis is not necessary. It's just that the proof that we're going to give now requires it, okay? But after the holidays, next week, like we're going to generalize this Maya-Vittora's argument, and then we can prove this theorem again, but without this hypothesis of finite type. Okay, so So in order to prove the theorem, we have to start with the base case, and so we're gonna first prove it for a product bundle, okay? And the theorem for a product bundle is called the Poincare lemma for compact vertical support. And so it says pi lower hatch from the cohomology with compact support, compact vertical support of a product bundle to the cohomology of M is an isomorphism. Now, actually, to prove this, you can assume that R is 1, right? So it suffices prove. Well, yeah. Oh, I should have a minus R here. Minus R. Okay, and then we just have to subtract. Okay, we can. It's enough to prove this because, then you can substitute it in M cross R for M, then you will have M cross R square. And then if you put in M cross R square, you'll have M plus R cubed, So we just need to prove it for M cross R. And, and the proof is, yeah, okay, then maybe I'll write down why it's enough to prove it, because then you can have, oh, just a minute. Oh, I guess I can't just do it for R. Yeah. Yeah, because like, if I have R square, that will actually go to K minus 1 with ordinary support of M cross R. Right, and so I actually can't, repeat the theorem, right? Because I'm missing the compact vertical support. Yeah, so no, yeah, we can't just do it for M cross R. I think we have to do it for M cross R to the R. Yeah, because this doesn't go down to something with compact vertical support. All right, so yeah, so I need to adapt my proof. Okay. Okay, yeah. So I think I can adapt my proof. So we want to find a map that goes the other way. And so we let rho of t dt1 wedge dot 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 So let rho of t be a C infinity bump function. When I write rho of t, I mean rho of t1 to tr. So let it be a C infinity bump function on r to the r. Okay? So that means it looks like this. It has a graph that looks like this. And we want the integral to be 1. And then we let E be rho of t dt1 wedge dot 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 dtr. So it is an R form. This is very much like the proof for Poincare lemma for compact support. Okay, and so now you just take a form on M and you wedge it with this. So you define E lower star from K minus R forms on M to A forms on M cross R to the R with compact vertical support. Okay, so yeah, E has compact support, and now I just wedge with E. So E lower star of eta is going to be E wedge pi upper star of eta. Okay, so I pull back this form eta to the product and I wedge it with E. Yeah, so now one of the things to keep in mind, that is that this E has dt in it. Okay, so in general, you should put the form with dt in it first. That way, yeah, you'll get the correct signs. So the form with dt comes first. All right. Okay, and now what is pi lower star composed with E lower star? What is that? You wedge with E, and then you integrate along the fiber. What do you think we should get? I mean, it's going to be pi lower star of E wedge, something that has only dx in it. Okay? And pi lower star is integration along the fiber. So you integrate out the dt's. And so what do you get? Yeah, because like this is like you're integrating rho t dt1 wedge dtr wedge pi lower star pi upper star eta, So this has only, the x's, and you integrate this and you'll get 1, and so you end up with something with just the x's. Okay? And so this gives you an inverse. Oh, yes, but then, yeah, we have to check the E commutes with, E lower star commutes with D up to sine. Okay, now E lower star, it has degree R. Yeah, so I didn't check this, but because I checked it only for degree 1, and the sign was -1. But I'm going to guess that in general, when you have degree R, then the sign should be this. Should be -1 to the R. Okay. Yeah. So, uh, so check this at home. Yeah, that better be the sign. Yeah. And so that's E lower star defined on the forms, it's a cochain map. And so it induces a map in cohomology, E lower hatch. And I mean, E lower hatch of a cohomology class is just the class of E lower star. Huh? Okay, so if pi lower star composed with E lower star is the identity, then the induced map should be the identity. Okay, so okay, so therefore, you have a pi lower hatch composed with E lower hatch is the identity. Okay, on yeah, HK minus R of M. Well, it's going to be in any degree, right? So I'll just put this. So we found an inverse on one side. And then we have to check that it's an inverse on the other side too. So I guess what we have found is a right inverse for pi lower hatch. And now we need a left inverse. Okay. However, if you do it the other way around, E lower star composed with pi lower star is not the identity. Okay? Yeah. Yeah, here we have the identity pi lower star, E lower star. Okay, but doing it the other way is not the identity. Okay? On forms, yeah, pi lower star, yeah, it goes from forms with compact support. But it's okay because what we want is not the identity on forms. We want the identity on cohomology. Okay. So how do you get? How do you get the identity on cohomology when it's not the identity on forms? What do you try to find? Yeah, you want to find a co-chain homotopy, okay? And this is very much like what we did before. So, yeah, we have to define a co-chain homotopy, and we first define it on a chart. So for a chart, U x1 to xn of m, we define a co-chain homotopy. So it should go from forms with compact support, compact vertical support on E, down to omega k minus r of m, right? I think. No, just a minute. We are over a chart. So over a chart, we have a product bundle. So U cross R to the R to, let's see, yeah, omega k minus R CV of U cross R to the R. Okay, so what we want is that dk plus kd should be the identity minus E lower star pi lower star. Right? Yeah. Yeah. Now when R is 1, it's exactly the same formula as for cohomology with compact support. And that was what I had prepared. You're right. Yeah, this should be K. Just a minute. No, just a minute. Yeah, it should be. It should just be K minus 1, right? Thank you very much. Yeah, because D increases the degree by 1, so K should decrease the degree by 1. So that this preserves the degree, because on the other side, yeah, you have the identity here, which preserves the degree. Yeah, that should be K minus 1. Yeah. Okay, so yeah, I didn't check it for, I checked it only for R equal to 1. So I'm, but I think the same formula should work. So let's see. What was the formula before? Yeah. Okay, so now a form, okay, here. Yeah, a form on the product, right, either has a whole set of DTs or it doesn't, so you again have type 1 and type 2 forms. So, and on type 1 form, we define it to be 0. So forms yeah, in omega k CV u cross r to the r are sums of type 1 forms would be f of x t dtl wedge dxj, where the cardinality of L is less than R. And then type 2 form would be f of xt dt1 wedge dtr wedge dxj. And so we define k to be 0 on type 1 forms. And then on type 2, so k of f of xt dt1 wedge dt r wedge dt xj. Yeah. Okay. Now, when we had just one dt, we integrated from minus infinity to t, f of x t dt. We call this u. So yeah, so now I think, well, okay. I think I need to check this at home, but here is what I think it should be. So it should be, yeah, just the Riemann integral. And then you integrate to T1 and then to TR. So that you still have a form with T's in it. And then you have dxj, and because this might not have compact support in the vertical direction, so you need to subtract like what we did before. So you need to subtract the integral, okay, when you go to plus infinity. So that would be this. And then yeah, that would make sure that you know, this will be zero at infinity. Yeah, but yeah, you yeah, but you when it's minus infinity, when these t's are very negative, you don't want to subtract, right? So you actually need to multiply by this function that we had before, which is looks like this in the one-dimensional case. You know, so that it's 0 near minus infinity, and then it's 1 near plus infinity, but we need the n-dimensional version. Okay, and then you still have the xj. Okay. To get the n-dimensional version, you just rotate this. Okay. Yeah, so I think that should be the formula. Um, oh, oh yeah. Oh God, yeah. So the all right, there is a problem there. All right, so I think I'll have to fix this next time. Yeah. Uh, um, oh, okay. So you are suggesting that that we integrate. So let's say we just integrate with respect to the first variable. And then we keep the other ones here. Like this? Oh, yeah. And then here we would just do the first one. And go from minus infinity to infinity. And then dt2 wedge dtr. That would have the right degree. And then maybe do it for all the other variables. Does anybody have any other suggestions? Like this looks like, yeah, you know, looks like a reasonable formula. All right, so we have to do this again next time. Yeah. All right, so, but the goal is to define this co-chain homotopy, right? And whatever the formula should be. And then once you have that, then you have the Thom isomorphism theorem for a product bundle. And now after that, then you need a Maya-Vittora sequence for compact vertical support. So let's look at that. Um, yeah. So let UV be open sets in a manifold M, and so we want to look at forms with compact support over the union to forms with compact support over U and formed with compact vertical support over V, and then forms with compact vertical support over the intersection. Okay, and then this map, I is going to be the restriction and J will be the difference. So it's just like for ordinary support. Okay? Yeah, it's not for compact support. For compact support, the Maya-Vittora sequence goes in the other direction. Okay? But this is compact vertical support, so there's no compactness hypothesis, on the base. And so you have these two maps, and then the theorem is that this is a short exact sequence. Short exact just means that it's exact, but it's got these 5 terms. And the proof is exactly the same as for forms, with no compactness hypothesis. Okay. So again, you need to use a partition of unity, and but here, these are upstairs, right? These are vector bundles, so they're upstairs. You just pull back your partition of unity upstairs, then it's like the same formula, okay? And so by the zigzag lemma, this induces a long exact sequence in cohomology. So this induces a long exact sequence in cohomology, and that is the Maya-Vittora sequence for compact vertical support. Now, I think I need a lot of room, so I'm going to use this board. So we have h k minus 1 of E over the intersection to hk of E over the union to hk with compact vertical support of E over U Okay. Yeah, so we have this long exact sequence. Intersection, union, hmm? um, no, because like this is restriction, right? Yeah, yeah. This is not compact support. Okay, yeah. For compact support, yeah, it goes in the other way because it's by extension by 0. Yeah, but this is restriction. And then this is the difference. Okay, yeah. So, and this is the upper star. Okay, and then we also have the Maya-Vittora sequence on M, and it goes in the same direction. Okay, now just a minute. So I actually want this to be R minus K minus R minus 1 and K minus R. And then K minus R. Okay, so we have these two Maya-Vittora sequences, and then integration along the fiber goes from the top sequence to the bottom sequence. So let's see, this is integration along the fiber over the intersection. This is intersection along the fiber over the union. And then this is intersection along the fiber over U and over V. And this is intersection, integration along the fiber over the intersection. Okay. So you have integration along the fiber from the top sequence to the bottom sequence. And we can check that, this diagram is commutative. So proposition, this is a commutative diagram. Yeah. And then this will allow you to get, so the Thom isomorphism, so like if you have the Thom isomorphism for the intersection and for U and V, then you will have this being an isomorphism, this being an isomorphism, so you have isomorphisms on both sides of the union, right? So just like before, we have this theorem that isomorphism for U, V, and U intersection V implies isomorphism for the union. Okay. And now we can start to do induction. So the base case, oh yeah. So we need this theorem that a vector bundle over a contractible space is trivial. Trivial means it's isomorphic to a product. So this is like the theorem we assumed before, that a fiber bundle over a contractible space is trivial, okay? The proof of this theorem is actually in the book, okay? But we'll just assume that. And so if you have a good cover, because every open set in a good cover is diffeomorphic to Rn, it's contractible. So on a good cover, a vector bundle is trivial over all finite intersections, over any finite intersection of the open sets in the cover. Okay. And now if you have just one open set, okay, the vector bundle is trivial, and provided that we have the right cochain homotopy, right? So that's the Poincaré lemma for a product bundle, and so you have the Thom isomorphism, and then we do induction on the number of open sets like before. Okay, so by inducting on the number of open sets in a finite good cover, for M, so the Thom isomorphism theorem follows. Okay, yeah. All right, so let's take a break for 10 minutes. So during the break, I was thinking about the disaster that struck during the first half of the lecture. And I think I know how to fix it now. I think what we have to prove is this. Um, um, yeah. Pi lower star from, um, let's see, no, pi lower hatch from the cohomology with compact support of m cross r to the r to the cohomology with compact support of m cross r minus 1 is an isomorphism. Yeah, because then it goes down by only one dimension. And so we can use the same co-chain homotopy that we had before. Okay. And this, because it goes from cohomology with compact support to cohomology with compact support, you can carry out the induction. So you can go from R, eventually to 0. But when you have 0, that just means that your bundle, has fiber a single point, okay? And so eventually you end up with HCV 0. No, just a minute. K minus R of M cross R to the 0, okay? Now this is a vector bundle whose fiber is a single point. And so it's just M itself. And so the compact support in the vertical direction is just the same as, no condition in the vertical direction. So you'll get this. Yeah. I think that's how you will fix, that's how we can fix it. Okay. And we can use exactly the same K as before, that goes down by just 1 degree. Yeah. So let's all do this at home, okay? See if it works. Yeah. All right. So I want to now prove a very useful property of integration along the fiber, and it's called the projection formula. Okay. So the projection formula, is in the setting of what we are looking at. We have an oriented vector bundle of rank R over a manifold M. And then suppose we have a form with compact vertical support on E and a form on the base. Okay, then pi lower star of omega, which now you have to bring tau upstairs. So pi upper star of tau is pi lower star of omega, wedge tau. Okay, that's the projection formula. It's a very useful formula. You know, in here, omega is the form with dt in it. Right. It's upstairs. Tau has only the x's. Okay? In this formula, yeah, the form with dt has to come first. Okay? If it comes first, then you don't have a sign. Okay? But if you put it behind the form without the dt, then there will be a sign. Okay? Yeah. So in general, always put the form with dt first. Okay. Now, okay, so why do we need an oriented vector bundle? Where do we use the hypothesis that the vector bundle is oriented? When it's oriented, it means that every fiber, which is a vector space, is given an orientation, right? So why do we need an oriented vector bundle? Right, yeah, we need that orientation on the fiber so that we can do integration along the fiber. When you integrate, you always need an orientation. Right? If you change the orientation, you get a minus sign, okay? Okay, and then you can only integrate, you know, if it has compact vertical support. Now this tau, it doesn't have any support hypothesis, okay? So what we have to prove first is that, you know, this is an arbitrary form, right? It may not have compact support, but omega has compact vertical support. So we first have to prove that when you wedge a form with arbitrary support with a form with compact vertical support, you get a form with compact vertical support, okay? Yeah. All right, so that's first what we have to prove first. Proposition. If sigma has arbitrary support on E and omega has compact vertical support, then the wedge product has compact vertical support, has compact. And the definition of compact vertical support is that, you know, you have to intersect the support with the inverse image of a compact set. So let K be compact in M. And then we look at the support of sigma wedge omega intersected with K, with pi inverse of K, okay? And the support of a wedge is contained in the intersection of the support and this is contained in the support of omega intersected with pi inverse K, okay? Now, because omega has compact vertical support, so we know that this is a compact set. And it's in pi inverse of K. Okay? And here, okay, the support is closed. Okay? So this is closed in E. And then you intersect it with pi inverse of K. So this is closed in pi inverse K. Since a closed subset of a compact set is compact, then we know that this is compact. So this. And therefore, the wedge product has compact vertical support. So that's. Okay. All right. So that just to show that the left-hand side makes sense. Okay? This wedge product has compact vertical support, and you integrate along the fiber. Okay. Okay. Now, in general, to prove the equality of two differential forms, what is the simplification that you can do? You want to prove that two forms are equal. Like if I give you any two forms and I say, show that they're equal. So the first step, you simplify it to what case? Well, two forms are equal if and only if they are equal at every point. So you can just look at a neighborhood of a point. Yeah, so to prove the equality of two forms, we can assume that we are in a neighborhood, in a small neighborhood, so like in a chart, okay? Yeah, so, and in a chart, then we know how to write down everything in terms of coordinates. So, so suffices to prove equality in a chart of U cross R to the R. And then the coordinates on U are x1 to xn. The coordinates in R are t1 to tr. And then omega. Oh, so yeah, if omega has type 1, that means it doesn't have enough t's then the wedge product will be type 1, so pi lower star will be 0. And here, pi lower star omega is 0. So if omega has type 1, then both sides are 0. Both sides of the projection formula are 0. Okay? So you can assume that omega has type 2. And that means omega is f of xt dt1 wedge dtr wedge dx j. Okay? Omega is the sum of terms of this form. And so the left-hand side is pi lower star of omega wedge. So tau it's going to be some function times the xi, or a sum of functions like that. Okay? And then we simply integrate out the t's, and we are left with h of x dxi. That's the left-hand side. And now, oh, I left out the xj, right? Yeah. Yeah. But let me see. So this part, that's just pi lower star of omega. And this is tau. Yeah, so this is pi lower star of omega wedge tau. Okay? Yeah, so that's the projection formula. Once you write it in local coordinates, it's very easy. Okay? Okay, now this has some implications for the Thom isomorphism. So the Thom isomorphism theorem says that pi lower star from the cohomology of the vector bundle with compact vertical support is isomorphic to the cohomology of M, but with degree R less. So because it's an isomorphism, then you can take the inverse. Now, this inverse is called the Thom isomorphism. And so it is going to take H0 of M to H0 with compact support, no, to HR with compact support of E. Okay? In H0M, there is a special cohomology class. What is it? In H0 of M. I mean, H0 is represented by constant functions, right? So among the constant functions, which one is special? One. Yeah, yeah. So there's one here, okay? And so this one will map to a cohomology class of degree D, of degree R, sorry. And what that says is that on any oriented vector bundle, there is a special cohomology class. And it is the image of one under the Thom isomorphism, okay? So, and this class is called the Thom class. Why? So definition. So this is an intrinsic class, you know? Whenever you have an oriented vector bundle, then there is this cohomology class called the Thom class. And so it has to be important because it's intrinsic. It doesn't depend on the choice of coordinates or anything. No? Yeah, so it's an important class. And then this vector bundle it has sections, right? But among the sections, there's one that is special. Which one is it? Like a section that doesn't depend on any choice. Like a vector bundle looks like this. And like every fiber is a vector space, right? Yeah, every vector space has a zero. So you have the zero section, which is special. And so, you know, the zero section S goes from M to E. And by pulling back, you have you know, cohomology of E going to the cohomology of M, okay? Now the Thom class is represented by a differential form, a closed differential form, okay? So it will define a cohomology class here too. And therefore, you can pull it back. And that's also very special because it doesn't depend on anything. And that is called the Euler class of the vector bundle. So the Euler class of the vector bundle, of the oriented vector bundle, is the pullback of the Thom class. And it's a cohomology class in M. Yeah. Yeah, so both of these cohomology classes, must be very important because they just come with the vector bundle without any choice. And later on, I hope I have some time to discuss the meaning of these classes. My professor likes to call this kind of things that doesn't depend on any choice, God-given. Okay? Yeah. He's Catholic. He's very religious. So these God-given things are really important. And then, finally, I want to show you one way in which the Thom class is useful, and that is, it allows you to write down explicitly the Thom isomorphism. Okay. So, yeah. So we have this formula, right? Like for any omega on the base, I want the formula for the Thom isomorphism of this omega. So look at this. So pi lower star of phi, which the pullback of omega by the projection formula is pi lower star of phi. Oh yeah, no, just a minute. Yeah. Okay, yeah. So phi is the inverse of 1 of pi lower star. And yeah, that means pi lower star of phi should be 1, right? So let's write this down. So from the definition, pi lower star of phi is the class of 1. Okay, so if you think of it as a differential form, it's 1, and that means, and this is integration along the fiber. So the Thom class is the unique cohomology class on E, okay, with compact vertical support that integrates to 1 on each fiber. Okay, and then here, yeah. So by the projection formula, you have pi lower star of phi, wedge omega, pi lower star of phi is 1, or the cos of 1, and then you wedge with omega, so you get omega, okay? And yeah, and so pi lower star inverse of omega is going to be phi wedge pi upper star of omega. Okay? And that says that the Thom isomorphism is the pullback wedge with the Thom class. That's it's pi lower star inverse is the Thom class wedge with the pullback. All right. So you have an explicit formula for the Thom isomorphism. Okay, so we'll stop here today.